All right, so continuing on with our section of 17, now let's think about predicting the magnetic field above and below many loops of wire. So if you had many loops, you would have your current going in, out towards you, and then back around and then in. And then what we'd see is you'd have a magnetic field going this way and through the center, and you'd have the opposite on either end. So at the outsides of the loops of wire, the magnetic field goes this way, and then you would have a different magnetic field going through the wire. Now let's look at the magnetic field of a thin and long coils. So we have a battery, the minus end, and a positive end. You connect current carrying wire, make several loops, like so. So this has N turns, and it's very thin. A coil of wire with N turns produces a magnetic field that is N times the field produced by one turn, which makes sense conceptually. And for this, you need to assume coil is thin and all turns are in the same plane. So if you have too many turns and you start to get a lot of volume, then this doesn't hold. Then you have something called a solenoid, and we do actually have a way to handle that. So a solenoid, you'll have, let's say you've got a long cylinder and you've got all of this wire wrapped around it, only the turns would be very, very close together. It would have length L and N loops. And the magnetic field of a solenoid is approximately mu naught Ni over L for a solenoid. And the derivation for this is in 17.4. And I'll go through, 17.14. I'll go through some of the highlights of it on where this is derived from. And there's a more beautiful derivation for the magnetic field of a solenoid once we get into the later chapters and learn about something called magnetic flux.